Right. So here in this diagram, you see the different parts of the human eye. Basically, what we are interested in is the lens. Okay, what is the shape of this lens? Convex or concave? It's clearly a biconvex lens. Fine. And the refractive index of the material with which the human eye is made, it's higher than refractive index of air and also the refractive index of what is present inside the eye. Okay, so the lens material is denser, optically denser. If lens is optically denser compared to the surroundings and it's a convex lens, then it behaves as a converging lens. That means it has a positive focal length. Okay, the lens in your eye, it always has a positive focal length. Okay, and behind the eye, there is a screen called the retina. Fine. Whatever image forms on the retina can be seen by us. Okay, so light from an object has to pass through the eye lens and its image must form on the retina. The whole thing that you see here is the eyeball. Okay, we can imagine it as a sphere roughly. So let's consider this diagram. Now see, your eye helps you look at many different objects which are at different distances from you, right? So visualize the principal axis. Assume this is the principal axis. You know where the lens is. So this point effectively is the optical center P. Okay. Now your eye should be able to show you the images or able to form images of many different objects in front of you, not just one object. So whether an object is here or here or here, it should be able to form an image on the retina. Okay. You can see where the lens is. And the size of the eyeball is fixed. Right? Now, if the size of the eyeball is fixed, it means the distance from the lens to the retina. Retina basically is like a screen for us. Okay. Distance from the lens to the retina is fixed. And you want like to be able to see clearly, the image must form on the retina, right? That means the distance between lens and image is fixed for a human eye. Okay. So image distance V is fixed. If image forms at that distance, only then you'll be able to see clearly. And your eyes definitely show you clear images of a lot of objects that are in front of you. Some of them are close to you, some of them are far from you, and you know that. Okay. So suppose you want to look at this object. Then what your eye does is, see, you can like from this itself, you can understand the image distance is fixed, but for the blue object, there's one object distance. For the orange one, there's a different object distance. And for the yellow one, there's a different object distance. But whatever be the object distance, the image distance is the same. How is that possible? It's possible. I mean, how is it possible to form an image on the screen for different objects which are at different distances? It's possible if it keeps adjusting the focal length. Okay. To form the image of the blue object on the retina, it should have a particular focal length. To form the image of the orange object on the retina, it should have a different focal length. Okay. Similarly for the yellow one. So for different objects at different distances, the eye must adjust its focal length to be able to form an image on the retina. Okay. I hope you are getting this. The lens formula is 1 by V minus 1 by U is equal to 1 by F. Now, for all objects that you see, the image distance is fixed. But objects are at different distances, so object distance is variable. Then if you must see the object clearly, then the focal length of the eye must also be a variable. Focal length of the eye lens must be a variable. How do you think the eye lens adjusts its focal length? Any idea? Any rough idea at least? How does the eye lens adjust its focal length? Okay. One of you tell me lens maker's formula. Formula for the focal length of a lens. Lens maker's formula.
So 1 by f is equal to n2 minus n1 by n1 into 1 by r1 minus r2.
Okay. Don't say 1 by r1 minus r2. It's 1 by r1 minus 1 by r2. Okay. Fine. Now, N2 is the refractive index of the material with which the lens is made. N1 is the refractive index outside the lens. Now, our eye cannot change that refractive index because material changing is not possible. Okay. The material of your eye lens cannot keep changing. So the first bracket N2 minus N1 by N1, this is fixed. Okay. That cannot be changed by the eye. What our eye does to adjust the focal length to be able to form images of different objects on the retina is that it adjusts the radius of curvature. Okay. The eye lens keeps getting flatter and more curved. The radius of curvature keeps changing depending on the object that you're looking at. Okay. And the muscles in the eye help us do that. Okay. So remember, the eye is able to show you, the human eye is able to show you clear images of different objects which are at different distances, even though the screen is at the same distance. That is because, or how does it do that? By adjusting its focal length. And you all must have observed this also. If you are focusing at one particular distance, other objects at other distances automatically appear blurred to you. Have you all observed that or not?
Yes, sir.
Even in cameras, digital cameras, it is seen these days. If you focus on something nearby, the objects which are far get blurred. If you focus on something which is far, the object which is near will get blurred. Okay? Because if focal length is set to a particular distance, that object's image will be forming clearly. Other objects which are closer or even farther, their images won't form on the retina. They'll form somewhere else. Okay? So that is why we clearly see some objects, and at the same time, some other objects will appear blurred to us. Fine. Now, like depending on the distance of the object, the eye adjusts its focal length to be able to form an image on the retina. That's fine. But for any of us, if the object comes too close to the eye, okay, like you consider an object like this fingertip very close to your eye will not be able to focus on it if it's too close. I mean, your eye will not be able to form a clear image on the retina if it's too close. Correct or not?
Yes, sir.
It cannot. Okay. There is a certain minimum distance, okay, at which an object should lie in front of you such that you can clearly see it. Means such that the eye can adjust its focal length and form an image on the retina. Okay. That minimum distance at which you can see objects clearly is called the near point distance, or shortest distance of distinct vision. Okay, denoted by the symbol capital D. Approximately, not approximately, on average, this is about 25 centimeters from the lens of the eye. For some people, it may be even shorter. They may be able to clearly see objects which are much closer than 25 centimeters. Some people won't be able to see clearly even if it is at a distance of 25. Their shortest distance of distinct vision can be more than 25 also. On average, it is 25. And if you are asked any questions based on vision, you have to assume that D is 25 unless otherwise specified in the question. Okay. So only objects which are at a distance of 25 centimeters in front of the eye or farther than that can be seen clearly by the average person. Fine. Now, there are some people whose eye lens cannot adjust its focal length that well. Okay. So their shortest distance of distinct vision may be some 30 centimeters or 40 centimeters or 50 centimeters. They may not be able to see anything closer than that. And sometimes the reverse also can happen. There are some people who can see things which are close to them, but cannot see beyond a certain distance. Okay, these are the two, what do you call, defects of eyesight. Okay, two common defects of eyesight. So first one, suppose the person is able to see objects which are close to them, but are not able to see far away objects. What is that defect of the eye called? They're able to see objects which are close to them, but are not able to see far away objects.
Myopia, sir.
Myopia, the common defect that most young people have. Fine. Now see, the eye lens is a converging lens, convex lens, and because it is denser, we can call it as a converging lens. Let me take an image of converging lens. Let's say this is the lens, and you know that the distance from the eye lens to the retina is fixed. Means distance from the lens to the screen is fixed. Image distance is fixed basically. Okay. Let this be the screen. Means image has to form here. Now, converging lens, what does it do? It bends the light rays towards the principal axis. Fine. If an object is too close to the eye, you imagine incident rays from it. One ray like this and one ray like this. See, if you remember these cases, no, then it will be easy for you to answer. So we'll spend some time on this. If it's too close, even if it bends towards the principal axis, it won't form a real image on the screen. The rays are not going to converge onto the screen. Okay. Usually no eye can see this. If the object is too close, we cannot see. Now, suppose the object is exactly at a certain distance, like the focal length. Then what will happen? A ray incident like this passes parallel to the principal axis after refraction. This way. Still, image won't be formed on the retina. That also cannot be seen clearly. It will appear, but it will appear blurred in your vision. Okay. Consider another object somewhere here. We are considering point objects only, but you know how to draw images of extended objects also. Same logic can be used. At the same distance, extended object images also will form. Now this ray has to bend towards the principal axis. Now the one coming from the blue dot was going parallel to the principal axis. Fine. Now from the green dot, if you see the ray which is incident, if it bends towards the principal axis, there is a chance that the image forms on the screen. Like there's a chance that it goes like this also, forming behind the screen. That possibility is there, but there is also a possibility that an image, clear image, forms on the screen. This is what we want the eye to do. And this is why there is a shortest distance of distinct vision for the eye. See, its focal length is adjustable, of course. It's not a fixed focal length, but still it can't adjust itself to any value that is needed. Okay, there are limitations. So this is why every eye has a shortest distance of distinct vision. This is what you call capital D. Okay, now to be able to see this green dot also, or to be able to form an image of this green dot on the retina, which is at that fixed distance, the eye has to adjust its focal length. Okay, for some, on average, okay, for humans, the focal length gets adjusted such that this object distance is 25 centimeters. And the image forms on the retina. I think eye lens to retina distance is about 2.5 centimeters or something. So that's the image distance. Based on that, object distance is 25. You can calculate focal length also. Okay. Suppose the object goes further away from the, what do you call, eye. If the object goes further away from the eye, if it maintains the same focal length, then image won't form on the lens. For example, consider this object. If the eye does not change its focal length, then what will happen? This dark blue ray that is incident converges more than the green ray. If it converges more than the green ray, then the image forms in front of the retina. Okay. But what happens is the eye adjusts its focal length such that that blue dot's image also forms on the retina. That will be a different focal length. Okay. Suppose you continuously take the object away from the focus, or away from the lens, not focus, sorry, away from the lens. One of you tell me, if object is at infinity, where does the lens form the image? If object is at infinity, very far away, where does the lens form the image?
Focus, sir.
At the focus, correct. Okay. Usually, yeah, okay, maybe I should not say usually, but if there is no defect in the eye, we can clearly see objects which are at infinity. Clearly means I don't mean to say in detail, but image will be formed sharply. It's a very small image that forms. If object is at infinity, the size of the image also will be very small. Okay. So I'm not talking about clarity in terms of details. I'm talking about clarity in terms of image formation. Image will be formed clearly, but it's a very small image. You can't see the details properly. So if object is at infinity, the rays which are incident like this, parallel to the principal axis, they converge on the retina. I mean, the eye will usually be able to, like, if there's no defect, it will be able to converge them onto the retina. Okay. So this is with a normal eye. But what happens if it is a myopic eye? Can any of you tell me? For rays which are parallel like this, where does the image form? In front of the retina, or exactly on the retina, or behind the retina? Basically, a myopic eye, what can I say? It has more converging power. Okay. If a faraway object like this is present, if rays are coming from infinity, what the myopic eye will do is it forms an image in front of the retina. It bends the rays too much. Or you can say it converges the rays too much. Okay, suppose there's a faraway object. It converges the rays too much and forms an image in front of the retina. Like this. That is why people having myopia cannot see faraway objects clearly. This is the reason. Now, how to correct for this? You see the problem. The problem is that there is too much convergence happening. Okay, so what is the correction for it? You have to make the rays diverge. Now you can't make the rays diverge after entering into the eye. So what you have to do is you have to make them diverge before entering into the eye. Okay. And to make them diverge before entering into the eye, what kind of lens you should use? A diverging lens, which is basically a concave lens. Okay. So if you consider a lens like this, okay, let me use a different diagram. Without the use of any lens, this is what would have happened with the myopic eye. Now, if you consider a diverging lens, you know the shape of the lens of your specs, it will be like this, but its focal length is negative. It's a diverging lens. So what this does is, instead of allowing light to pass like this, okay, this is how it would have passed had there been no specs or lens used. Okay. Now this lens diverges light before entering into the eye. This is what it does. And now see this the eye lens has a tendency to converge too much. So what we are doing is we are making divergent rays enter into the eye. Now it will use its ability to converge, and it can converge this exactly onto the retina. That is what happens. So this is how we correct for myopia by using concave lenses. Fine. Focal length negative, that means power also has to be negative. So this is why we use a concave lens or a diverging lens to correct for myopia. So remember the problem and the solution. The problem with the myopic eye is that it forms an image in front of the retina. For far away objects, it forms an image in front of the retina. It has too much converging power. Okay. So we have to decrease its power basically. So how to do? It has too much converging power, positive converging power. So we give it some negative power. So we add a lens in front with negative power, negative focal length, and that is what it does. Next, suppose the eye does not have the necessary converging power to form an image on the retina or in front of the retina. Consider another ray like this incident parallel to the, okay, consider some other rays incident parallel to the principal axis. These rays, suppose they cannot be converged onto the retina or in front of the retina. So basically something like this happens. Then what will happen? Image of faraway objects forms behind the retina. This is what happens in a hypermetropic eye, or this is what you call hypermetropia. Fine. Their eye lens does not have sufficient converging power, does not have sufficient converging ability. Okay. Can one of you tell me how to correct for that? Pradyum, think carefully and answer. Don't be in a hurry. Concave is used to correct for myopia. Okay. See, here the problem is that their eye lens is not able to converge light properly. Okay. Or converge light sufficiently. So what we need to do is we need to converge the light a little bit before it enters into the eye. Okay. That is how we can enable them to see things clearly. So here what kind of lens will be used? A converging lens will be used. Okay. Usually aged people will be using lenses like this. Those lenses show convex behavior or converging behavior, positive focal length. Positive focal length, power also will be positive. Now what that lens does is, it converges the light a little bit before it enters into the eye itself. So this is how the light would have traveled had there been no lens. Now if you use lens with positive focal length, converges the light a little bit before entering into the eye, and the remaining whatever convergence is needed will be taken care of by their eye lens, and the image will form on the retina and they'll be able to see it. Okay, so this is how we correct for hypermetropia. Okay, are these two cases clear to all of you? Any doubt in this? Isha, did you understand?
Yes, sir.
Okay, Rishi, is it clear?
Yes, sir.
Fine. Let's solve some problems based on this. First, the nearest distance of distinct vision for a person is around, okay, fine. Nearest distance, let it be 25 itself. The farthest distance where a particular person is able to see clearly, okay, that's called as the far point. Nearest distance where we can see clearly is called the near point. Farthest distance where we can see clearly is called the far point. For a for a non-defective eye, far point is infinity. Okay, in fact, it is very relaxed to see objects which are far away. It is very relaxing for the eye to see objects which are far away, because there won't be much stress on the ciliary muscles. There won't be much stress on the eye lens. It will be in a relaxed position when object is at infinity. Image forms at the focus, it forms on the retina. Okay, that's the relaxed position of the eye actually. To see nearer objects, okay, or objects which are at finite distance, there will be a stress on the eye. Okay, usually when you sleep, no, your eye lens will adjust its focal length such that you can see objects which are at infinite distance. Means the focal length of your eye lens becomes approximately equal to the distance between the lens and the retina. Fine. When there's no stress on your eye, okay, stress or strain, whatever you call it, on your eye, its focal length will be this much. Okay, if object is at infinity, you'll be able to see it. To see objects which are at finite distances, the ciliary muscles need to adjust the focal length of the eye lens such that the image forms on the retina. Okay, so for a non-defective eye, the far point is infinity. Let's say there is a myopic eye. Okay, myopic eyes can be able to see up to a certain distance. Beyond that, they cannot see. Suppose the far point for a person is, let's say, 100 centimeters. Means if an object is beyond 100 centimeters or farther than 100 centimeters, the person's eye cannot form a clear image of it on the retina. That is what it means. Calculate the required power of the lens the person must use to see farther objects, or to be able to see farther objects. Think about it. The person's eye is able to form images of objects only if they are within this 100 centimeter distance. If the object is beyond 100 centimeters, the person's eye is not able to converge the rays onto the retina. Any idea, anyone? How are you going to solve this problem? If an object is farther than 100 centimeters, the person's eye is not able to focus this, is not able to converge those rays and form an image on the retina. Okay, I got one answer as f is equal to 100. We'll discuss. See, the solution here is if there's a faraway object, okay? Far away means not at infinity, any distance greater than 100. If there's an object like that, what the lens should do, what the specs, okay, the extra lens should do is that it should form an image of this object within 100 centimeters. That object's image should be formed somewhere here. And if it's formed within the distance up to which the person is able to see, then the person will be able to see. Okay. So whatever lens the person is using, whatever extra lens the person is using, it should form an image of that object within 100 centimeters. That is what should happen. Okay. Now see, the problem here is myopia. Person is able to clearly see up to 100 centimeters, but not beyond that. The problem here is myopia. Correction for myopia is done using a concave lens. Okay. Or a diverging lens. Concave lens or diverging lens. Fine. What kind of images does a diverging lens form?
Virtual image.
Always a virtual image. And what about magnification? Will it form enlarged images, diminished images? Okay, let's quickly recollect the image formation by a diverging lens for an extended object, of course. So suppose this is the object. Let's mark the focus. I took object on right side, so rays will be going to the left. Left side is positive. Anything on the right side is negative. Diverging lens has negative focal length, so this is the focus we are interested in. Okay. Take one ray parallel to the principal axis. After refraction through the lens, what happens? It passes as if it is emerging from the focus. It bends this way. The other ray we take is straight to the optical center, directly to the optical center. It passes without any deviation. This one. So if the eye is on the left side, if the observer's eye is on the left side, just a moment, the rays will appear to be coming from here. Okay, this is where the image forms. And since image is on the same side as the object, and refracted rays are not passing through the image position, this is a virtual image. Okay, and you can see it is upright, of course. The orientation of the image is same as that of the object, and it is diminished. Fine. People using concave lens or people using lens of negative focal length always see things smaller than they are. Okay, that is what the lens does. If they want to see things clearly, they will have to see them smaller than how they actually are. Okay, and see a concave lens, which is basically a diverging lens, always forms the image within the focal length. Fine. If object is at infinity, image will be at focus. Any object at a finite distance like this, image will be within the focal length. Okay. Now what we want is that this person should be able to see any object which is beyond 100 centimeters also, but the person can only see up to 100 centimeters clearly. So for all objects which are beyond 100 centimeters, the images must form within 100 centimeters. And we know that a concave lens or a diverging lens forms images within the focal length. We want to form images within 100 centimeters. The diverging lens forms images within focal length. That means this 100 centimeters itself should be the focal length of the diverging lens. And because it's a diverging lens, focal length is negative. That means f should be equal to minus 100 centimeters. That 100 is the magnitude of focal length. Any object beyond that, its image will form within this distance. Is this clear to all of you? And any object within this distance, okay, suppose there is one object somewhere here itself at 50 centimeters, that the person's eye will be able to show directly. So the person should remove their specs and see. If they see with specs, then it will be strenuous actually. When the object is within the distance, within their near point distance. Okay, wait, I should not call near point. This is far point. If the object is within the far point distance, it should be seen without specs only. Is this clear to all of you? Any doubts in this? Rishi, did you understand?
Yes, sir.
Okay. Basic idea is that a diverging lens forms an image within the focal length. Now for this person, we want the image to be formed within 100 centimeters. So 100 centimeters itself should be the focal length. Then you can write focal length is equal to...
Is the image always a virtual image?
Yes.
Okay.
Object is in front of the person. Image also forms in front of the person only. Okay, means on the same side of the lens. So focal length is minus 1 meter. Therefore, the power in diopter should be inverse of focal length. That will be minus 1 diopter. So the power of the lens that the person must use is minus 1 diopter. Okay. Fine. I think that much is enough about human eye. Basically, you have to remember what are the two common defects, myopia, hypermetropia, and how to correct for them.